ME347, Example 13. Air escapes from a tire through a hole with a diameter of 0.01 inches. The initial pressure in the tire is 90 psi-G, or gauge pressure. The temperature of the air in the tire is 70 degrees Fahrenheit, and the initial tire volume is 26 cubic inches, which can both be assumed constant. Estimate the time needed for the air pressure inside the tire to drop to 45 psi-G. Finally, sketch the TS diagram for this process. For this problem, we will first assume that the air in the tire is an ideal gas with constant specific heats. Second, we assume the air temperature inside the tire and the tire volume remain constant. Third, we assume uniform stagnation properties inside the tire at each time. Fourth, we assume uniform properties at the hole, or throat, and that the process is isentropic up to the hole. Note that we did not assume steady state because this is a transient process. To begin, we draw a schematic diagram of the problem. As stated in the assumptions, the air inside the tire has uniform stagnation properties at each time. Initially, at t equals 0, the stagnation pressure in the tire is 90 psi-G, which corresponds to 104.7 psi-A. We are calculating the time, T sub f, it takes for the stagnation pressure in the tire to reach 45 psi-G, which corresponds to 59.7 psi-A. During this process, the temperature is assumed to remain constant at 70 degrees Fahrenheit, which corresponds to 530 degrees Rankine, and the volume to remain constant at 26 cubic inches. Finally, the properties for the flow exiting the hole are indicated by the subscript E for exit plane, and the air outside the hole is at an atmospheric pressure of 14.7 psi-A. Note that we are converting to absolute units because for the temperature and pressure ratios calculated later, we must use absolute units. Before we begin calculating the time for the discharge process, we check for critical or choked flow conditions for the air escaping through the hole. Starting from the isentropic flow relation for critical flow, we see that the pressure ratio required for air to be at the sonic velocity at a throat is 1.893. At this pressure ratio or above, the flow will be choked and remain at critical conditions at the throat. To see how this limit corresponds to the air escaping the tire, we calculate the pressure ratio corresponding to the final time and get 4.1, which is significantly higher than 1.89. Thus, we can assume the flow will remain choked as it flows through the hole or throat for the entire process. Next, since we want to calculate the time for enough air or mass to leave the tire for the pressure to drop from 90 psi-G to 45 psi-G, we apply conservation of mass to a control volume that contains all the air inside the tire. For the first term, because the properties are assumed uniform at each time in the tire, and the volume is assumed constant, the term reduces to the change in stagnation density of the air inside the tire with respect to time times the constant volume of the tire. Note, in reality, the volume of the tire would typically decrease with time, which would make this problem impossible to solve analytically. However, this is a reasonable assumption to make to get an engineering estimate for the time. For the second term, for uniform properties across the exit plane, and for a hole of constant diameter, the term reduces to the density times the velocity times the area of the exit plane. Again, the actual area of the hole would typically decrease with time. Note that this final equation indicates that the change in mass in the tire is equal to the mass flow rate leaving the tire as expected. Note, in order to integrate this equation, we need relationships for how exit properties change with time. First, we recall that the exit properties will be the same as the critical or choke flow properties. Thus, these relationships can be obtained from the isentropic flow relations for critical conditions as shown. For the density, the ratio of the stagnation to critical density is the constant value of 1.577. For a constant stagnation temperature, the velocity remains constant at 1,030 feet per second. which is very fast. Note that the assumption of constant stagnation temperature corresponds to the limiting case where there is sufficient heat transfer between the air in the tire and the surroundings to maintain a constant temperature in the tire. Note that even though the temperature in the tire is constant, the exit temperature will be at the much lower critical temperature. Substituting these into our equation for conservation of mass, we get an ordinary differential equation that can be solved by integrating from our initial time at t equals 0 to our final time at t equals t sub f. Before we do so, we define a ton constant tau for our discharge process in terms of the process variables that is calculated to be about 42 seconds. Looking at our result, we see that the density will drop exponentially with time. Solving for the final time, we get the following relationship. Next, instead of calculating the densities directly using the ideal gas law, we use the ratio of the densities along with the ideal gas law to show that the density ratio and the pressure ratio are the same for an isothermal process. Thus, from our known pressure ratio, the estimated time for the discharge process is about 24 seconds. Finally, we plot the TS diagram that corresponds to the process of the air discharging from the inside of the tire. To begin, we add a line for the constant stagnation temperature at 70 degrees Fahrenheit. Next, we add a line for the corresponding constant critical temperature at minus 18 degrees Fahrenheit. Then we add isobars for the following stagnation conditions. Initially at P01, at the final time at P02, at the pressure when the flow ceases to be choked, which we calculate to be 27.8 psia, and at the back pressure at an atmospheric pressure of 14.7 psia. Finally, we add lines for the process at the initial time, the final time, and the time when the flow ceases to be choked. Note that at the first two times, the air expands isentropically, indicated by a vertical line, to the critical condition at the hole. Then it expands non-isentropically, indicated by a dashed line, to atmospheric pressure outside the tire. Below the threshold for choked flow, the air will expand to the atmospheric pressure at the exit. For these conditions, to obtain a solution, you must numerically integrate the resulting equation for conservation of mass.